So do we have a name for them? That's pretty good start. How would you name them? You call them. What would you call them? You would call them. What do they call them at the top? You call them chiral, or you call them enantiomers. So what you just built are two enantiomers of each other. Enantiomers, these are not enantiomers. How do you know if it's an enantiomer? The way you determine if they're enantiomers is by drawing the original and then drawing its mirror image. If the mirror image superimposes on the original, you could rotate it however you want, then they're identical. They are not enantiomers. The definition of an enantiomer is they're non-superimposable mirror images. So if you draw this box with the blue corner and you draw its mirror image, the blue corner down here, try to mentally rotate this box so that it superimposes. And you'd find when you rotate this one 180, the blue corner ends up on the wrong side. And so these are non-superimposable mirror images.
I forgot her name, the doctor that came to talk. She had a good way of explaining it. She said that like enantiomers would be like shaking your hand and giving a right hand to a right hand versus like...
Yeah.
It was really cool, like the way she explained it.
Yeah. There's another common one. This is enantiomers here, chiral. But it's basically the easiest. Example would be the left hand and the right hand. You know, the right hand is a mirror image of the left hand, but will they superimpose? That's it. They don't superimpose. And so these would be enantiomers, and it would be chiral. chiral. Enantiomers and chiral. And so what you did was you built two enantiomers of the molecule. All right. When light interacts with molecules, what does it interact with? Let's say electrons. And so it depends on where the electrons that it interacts with here. So on one enantiomer, let's say one bond is positioned this way, right? And so light's going to come in, and then light's going to interact this way, right? But in the other enantiomer, the bond is on the opposite side, and so when light comes in, it interacts this way. And so it depends on the enantiomer you look at. Light is going to interact either this way or the opposite. And so we call these optical isomers. Optical isomers is because it rotates. One enantiomer will rotate light one way because the electrons are oriented this way. The other enantiomer rotates light this way because the electrons are the opposite. Right? And so optically active. Usually you have a 50-50 mix of these optically active isomers, and it ends up not rotating light either way because they cancel each other out. But in terms of biological activity, you know, a lot of these substrate, you know, the reactant is called the substrate, and then you have the enzyme, right? And so the enzyme is going to have a site for each atom. And so if we look at an enzyme here, and then we'll arrange a site for A. A should go here, let's say B should go here, and C should go here. And so when we look at these two we'll have D up here. And so here's one where the A matches the A, the B matches the B, and C matches the C. It's supposed to. Do you see that? But what about its mirror image? Will its mirror image work with the same enzyme? here. And so if we do the mirror image of this, we'll put C over here, then B sticking out here, and then A going back here, and then D up here. And then we'll rotate it. We'll try to match A. But when we match A, if I rotate this 180, A matches, but will B match? Now because B's now over here and C's back here. And so when we have a mixture of enantiomers, only one of the enantiomers will interact with biological systems. This one. This is why, you know, stereoselective synthesis is so key, because if you're making a drug, you end up making both. Did she talk about this?
Yes.
You end up making both. And like when you take, let's say you take Advil, you know, half of it's wasted, basically. Or, you know, you'll have less side effects if you have optically pure, etc. And so this is a big field, and chemistry. So when you're doing this, you got to look at the orbitals and how it's synthesized. All right, so now we're going to go to the next challenge here. The next challenge is how many isomers, you know, and we only have what? Now we have geometric. Geometric isomers, what are the types? Cis, trans, mer, face. Each of those geometric isomers needs to be tested for the second type, which is, well, the stereoisomers is just one collective term used for, needs to be tested for enantiomers, or chirality, or optical activity. In other words, each of those you should make or draw the mirror image and see if it superimposes or not. And then in that way we could figure out the total number of isomers for each structure or each formula, right? All right, so here, the first one you're going to do is this. A. Trisethylene cobalt 3. The second one you're going to do is this. How would you name this? Wow. Finals coming up next week. But you're lucky. You know, how many nomenclature questions will I ask on the final exam?
One.
Probably one. Maybe two. If I decided to make it like 20% nomenclature complexes, I think you'd be in for a tough time. Yeah. Really tough time.
Oh, that was like the first week.
But yeah, I know it's the first week of the semester, so it's all a blur, memory, faded memory. But anyway, dichloro, bis ethylene diamine, cobalt 3. Well, tell me all the isomers for the tris, you know, and name them, and then for the bis. And it helps to build the models. I mean, if you think you have an isomer, you can always build it and see if it superimposes or not. Or you could try rotating it in your mind or on paper to see what happens. So give this a shot and see.